Hello. In this video, we are going to discuss the Jones-Faithfull representations of symmetry operations in a point or space group. Let us take an arbitrary point, x, y, and z. We can interpret these x, y, z values as coefficients, coordinates in some particular coordinate system. Here is the natural basis I, j, k. So x is the coefficient of the I vector, y is the coefficient of the j vector, and z is the coefficient of the k vector. Now let us have a symmetry operator r, perhaps a rotation, transform the point x, y, and z, and see what that becomes. We can interpret this transformation in light of the basis vector representation that we had seen in our previous video, and you can look right here in case you haven't seen that video yet, as interpreting what happens to each of the three standard basis vectors under this rotation. So the rotation will take I to I prime, j to j prime, and k to k prime. One very subtle and important point that I did not mention last time is, if this is the way that we interpret the transformation, one value of it is that the coefficients x, y, and z do not change. They are identical to the versions that we had before the rotation. So in effect, we're keeping the coordinates the same, but rotating the entire coordinate system underneath it. We can write down a representation for this transformation where we have this particular row vector where I prime, j prime, and k prime are column vectors, and each of those vectors is the new basis for the coordinate system. But we could also interpret the transformation so that the new transformed point is x prime times I plus y prime times j plus z prime times k. So in this particular interpretation, the coordinate system is identical to what it was before, but we have changed the coordinate values, the coefficients. Instead of x, we now have x prime. Instead of y, we have y prime. And instead of z, we now have z prime. This gives us the so-called Jones-Faithfull representation. And as we might imagine, we'll be able to use this to write down a representation for the rotation. When we use the Jones representation, now instead of using braces, we have parentheses. And now we are going to interpret each of these entries as a row vector. So this is actually a column vector where x prime is the first row, y prime is the second row, and z prime is the third row. For our first example, let's look at the C₂ rotation around the z-axis. As we had shown in some detail in the previous video, the effect of this C₂ rotation around the z-axis is to take the I vector to the minus I vector, the j vector to the minus j vector, and for the k vector to remain unchanged. So the point that had originally begun as xi plus yj plus zk is transformed by the C₂ rotation to x minus I plus y minus j plus z times k. And then recall that the minus I, minus j, and k would form a basis vector representation. But now we want to see how we can write down the Jones-Faithfull representation for the exact same transformation. First step is to rewrite what we already have in a slightly more suggestive way. So now that I have it as minus x times I, minus y times j, plus z times k, it is helpful to write it in such a form that we have I, j, and k clearly delineated from each other and written from left to right. To find the x prime here, I look at what is the coefficient, the new coefficient of I in my expression. And I see that the coefficient of I is now minus x. X prime means what is this, the new coefficient of the I vector after the rotation has taken place. So we see in this case it's going to be minus x. Similarly, the value for y prime is going to be the new coefficient of the j vector. And since the new coefficient of the j vector is minus y, the y prime is equal to minus y. And then last but not least, the new coefficient of the k vector is our z prime. And since that hasn't changed at all, that's going to remain as z. Therefore, my Jones-Faithfull representation of the C₂𝓏 rotation is this expression here, minus x minus y z. And note very carefully that we do not have commas in between. Each of these is a row vector, and it is not a point. Our representation for C₂𝓏, as we've written down here already, just go right up here, we have minus x, minus y, and z. And now we'll see what this means in terms of a straightforward, literal 3x3 matrix. Minus x is the first row, so since it's minus x, it's minus 1, 0, 0. If it had just been ordinary x, it would be 1, 0, 0. Our second row is going to be minus y, so that's going to be the row 0, minus 1, 0. If it had just been positive y, we would have had the row 0, positive 1, 0. And then our final row is going to be 0, 0, 1. So notice that for whatever particular, if it's x, we're going to have it in the first column, y is going to be in the second column, and then z is going to be in the third column. I also refer you to look at the 3x3 matrix that we had generated by the basis vector representation, and we notice that even though it looks different, that the actual 3x3 matrix is identical. It is also identical to the matrix that you would get by using the traditional cosine of theta and sine of theta formula. For our next example, we're going to look at the C₃ rotation around the point x equals y equals z. We recall from our previous video that this particular rotation takes the I vector into j, j into k, and then k back into I. So I goes to j goes to k, and then k goes to I. So if we start with the arbitrary point xi plus yj plus zk, it gets transformed this way. Because notice the I gets transformed into a j. That's that transformation. So x stays there, but I goes to j. Similarly, j goes to k, so we have y times k. And then k goes to I, so we have now z times I. So this is the first step of the basis vector representation, which we need if we want to continue on as well to the Jones-Faithfull representation. But this at least gives us how the basis vectors transform under the rotation. In the next step, we merely rearrange it so that we have the I vector first, the j vector second, and the k vector third. So we're just rearranging this using the commutative property of vectors. But now we have some coefficient times I plus some coefficient times j plus some coefficient times k, which is what we're going to need for the faithful representation. To find x prime, the new value of the x coordinate, we simply look at what is the coefficient of the I vector. And the I vector coefficient in this case happens to be z. So x prime is going to be z. Similarly, if we want to find the new value of the y coordinate, I simply look at what is multiplying the j vector. Multiplied times the j vector is a coefficient of x, So that is our new value for y prime. And then for the z prime, the new value of z, that is going to be the coefficient of the k vector. Therefore, the z prime is going to be equal to y. So this means that we can write down a representation for the C₃ rotation that's going to have the rows. The first row is going to be z. The second row is going to be y, because that's the y prime. It's going to be x, I'm sorry. That's for the y prime. So this is going to be x. And then z prime, our final column, is going to be y. So this is the Jones-Faithfull representation for the C₃ XYZ rotation. And just to write it in explicit detail up here, the Jones representation of C₃ XYZ is ZXY. So let's see what that is explicitly as a 3x3 matrix. Our first row is going to be z, so z is 0, 0, 1. The second one is x. X is simply 1, 0, 0. Instead of writing it as a column vector, we're writing it as a row vector. And then y, if it was the natural basis j, it would be 0, 1, 0, but now we write it as a row, so it's going to be the row 0, 1, 0. And again, notice that this is exactly the same 3x3 matrix that we had when we had derived the basis vector representation for C₃ XYZ. For our final example, we're going to look at the rotation C₄ around the z-axis. So recall that this rotation takes the I vector to the j vector, it takes the j vector to the minus I vector, and leaves the k vector unchanged. So that means it takes this particular point up here to x, but now I went to j, so we have to replace that by j. We have plus y, but k has now turned into, j has turned into minus I, so we need to write down minus I here. And then finally, we have z times k, and k has not changed at all, so it's still k. So this tells us that our transformed point is going to be x times j plus y times minus I plus z times k. Let us simply rewrite this in such a way that the expressions for I, j, and k go in order. So we have our first example, we have y times minus I plus x times j plus z times k. Note that all we've done here is just rewrite this particular expression so that we have I, j, and k in order. So how do we find what x prime is? X prime is the new coefficient of the I vector, which is going to be minus y. Minus y. I'll write minus y that way. The new value for y prime, is going to be whatever the coefficient of j here is, and that turns out to be x. And then the z prime, the new value for the z coordinate, is going to be the coefficient of the k vector, which is just the z from before. That has not changed. That means our representation for the C₄ z rotation is going to be minus y, x, and z. Now, to be clear, let's write this out as a 3 by 3 matrix. So our first row is going to be minus y. So that's 0, minus 1, 0. Our second row is going to be the x vector. So that's just 1, 0, 0. And finally, our z vector is 0, 0, 1. Again, notice that this is the exact same form of the 3 by 3 matrix that we would get using the traditional method or having used the basis vector representation, except that when we write it in a shorthand form, we're writing it where each of these expressions is to be interpreted as a row vector, whereas in the basis vector representation, each of the terms is to be considered a column vector. The Jones-Faithful representation also has the advantage that we can define a multiplication law, which simplifies the multiplication of the representations. In this particular case, we do the multiplication from the left-hand side, whereas with the basis vector representation, we did the multiplication from the right-hand side. If we have some row vector x prime times the representation ABC, the value is going to be a. So when we see x prime, it means just take whatever the first row is and then write that down. So x prime here we interpret as pick the first one. If we multiply by y prime times ABC, we interpret the y prime as pick whatever the second character is and write that down directly. Finally, z prime means interpret this multiplication as just pick whatever the third expression is and write it down exactly as it is. So this allows us to multiply 3 by 3 matrices very, very quickly. And we'll finish off this video by showing some concrete examples of the multiplication law in action. First, we recall that the Jones-Faithful representation for C2 around the z-axis is going to be minus x minus y z. So if we multiply C₂𝓏 times C₂𝓏, we have minus x minus yz times minus x minus yz. And now we were trying to multiply them quickly and efficiently, making use of the multiplication law. So we start at the left-hand side, and our first expression here is minus x. So minus x essentially means pick whatever the first value here is and write it down without any change, except for the fact that we flip the sign. So since this is a minus x, we transform it into a positive x. So this character here, the minus means flip the sign, the x means pick whatever the first thing here is, and then that is our expression. Similarly, our second expression here, we have minus y. That means the minus means flip the sign of the thing we have, and y means take what we have as the second expression. So we have this minus y here means take minus y and flip the sign, and it becomes positive y. Finally, and more simply, the final column is, a final row vector here is z. Z means take whatever the third expression is in this representation and write it down exactly as it is. So the third one happens to be a z, so we write down z. And as we note, the result of this is xyz, which is simply the identity representation. And we know that's true because we know that if we do a 180-degree rotation followed by another 180-degree rotation in the same plane, we get back where we started from, and that gives us the identity. For our next example, we note that the Jones-Faithful representation for C₄ z is going to be minus y x times z. So now let us see the effect of two consecutive C₄ z representations. So here we have C₄ z times C₄ z. So we have minus y x z times minus y x z. The minus y means take whatever the second expression here is and then flip the sign. So that's going to give us minus x. Here we have an x. That means take whatever I have as the first expression here and write it down without any change at all. So that's going to be minus y. And then the z tells us take whatever the third expression here is, and that just happens to be a z without any change. So see how quick that was. We're able to write down that the representation for the product of two C₄𓏏's is going to be minus x minus yz. And we've already seen that this is C₂𓏏. So it does give us exactly the result that we expected. Now for a more challenging and interesting result, let's look at the C3 rotation around the x, y, z axis. And we saw that the Jones faithful representation is zxy. So now we want to see what happens if we do two consecutive C3s around this line. So C3xyz times C3xyz is going to be zxy times zxy. And let's see what that gives us as a result. Well, we have z times, so z is our first expression here. That means take whatever the third character is and write it down exactly as it is. So third character here is a y, so we write down a y for the product. This x here tells us to take whatever the first character is and write it down without any change. So that tells us that the multiplication involving this x here gives us a z as a result. And finally, this y tells us take whatever the second expression is on the right hand side here and write it down without any change. So that gives us an x. So the product of two consecutive C3 rotations is going to be a matrix yzx. And what I'm going to tell you, which you'll have to take on faith for a second, is that this is equal to C3xyz to the minus 1. If these two are counterclockwise rotations, then this is a clockwise rotation in the opposite direction, obviously. But since we see that this is the inverse of a C3xyz, I can prove that this actually is C3 to the minus 1, because if I multiply anything by its inverse, I'm going to get the identity matrix as a result. So let's test that out to prove that this really is C3xyz to the minus 1. So zxy is our C3xyz. Our yzx is exactly our C3 to the minus 1. And now let's multiply it out to see that it really does give us the identity. Well, again, we multiply by the left. This z character says take whatever the third term over here is. So z, x is first, y is second, z is third. Take whatever the third character is and write it down without any change. So that's going to be our x. Kind of being inconsistent in my use of colors here, but that's not important. This x says take whatever the first character is over here and write it down without any change, and that's going to be our y. And finally, this y means take whatever the second character is to the right and write it down without any change, and that is z. And this is identically the identity matrix, showing that this particular representation, yzx, is the representation for the C3xyz to the minus 1, the C3's inverse. I thank you very much for your kind attention. Have a good one.